Welcome. We're now going to do a work through of Dynamics Worksheet 4C3, Mechanical Energy and Power. Question 1 is a definitional question, so I'm leaving that part to you. Question 2 is a basketball being dropped from a height. So let's take our information and put it onto a diagram and then be able to work with it. So let's just firstly, excuse me, the basketball has a mass of 0.45 kilograms. Remember, we don't work in anything other than kilograms. And it's going to be dropped from a height of 2.4 meters, and it's going to hit the ground, okay? So remembering in this situation, we are assuming that in all of these situations that mechanical energy is conserved. In other words, there is no loss of any energy out of the system because or due to a force acting against the motion such as friction or air resistance. So at the top of the place up here, the top of the path, we get mg delta H as the potential energy. And we can calculate that as 0.45 times 9.8 times delta H, which is 2.4. And if we calculate that with our calculator, which I had to go and get, we can calculate the potential energy at the top of that path is 0.45 times 9.8. And we're assuming that this is the zero level of the actual potential energy. So at this point here, we are saying that it's 0. Hence, it's only 2.4. So 2.4. And that gives us 10.584 joules. I'm going to keep that as 10.584 because I don't know if the answers that I've used have actually included how many decimal places. Right, now that means at the top of the path we have U being 10.6 joules and K equaling 0 because it's being dropped. At the bottom of the path, U is now going to be 0 because remember I said this is the 0 level, and K would have to be 10.6 joules because the total has to remain the same all the way down. Okay, and it doesn't matter where we are on the path. The sum of the sum of the potential energy plus kinetic energy must always equal this value there. So we can now work out. We can answer question A is what is the kinetic energy at the bottom of the path? Well, the kinetic energy at the bottom of the path would have to be 10.584 joules. Okay, I'll just see how many, yeah, I haven't rounded. So 10.58 joules. And we can use this now to work out the velocity that it strikes the ground, because if we know it has this kinetic energy, we can work out its velocity, because B says the kinetic energy is a half mv squared, and that means that 10.584 would equal a half times this mass, which is 0.45 times v squared. So that's messy. I'll just read 10.584. Right, I'll stop being a mess. Okay, multiplying this up, we get a expression for v squared, which is 2 times 10.584 over 0.45. Solving that now, we get 2 times 10.584 over 0.45, and that's 47.104. And square rooting, we get V equaling 6.85, it's 86 meters per second. Okay, which I think in the answers I've rounded to 6.9 meters per second. Okay. The beautiful part about physics is that we can often work out things in a different way, and we are now asked in 3 to confirm our answer using an equation of motion. So using an equation of motion, we're going to drop using U, V, A, S, and T. At the top of the path, our initial velocity is 0. We don't know the velocity. We want to find the velocity as it strikes the ground. We know the acceleration is 9.8, and we are going to use the downward direction. So we're going to use that up is positive and down is negative. The displacement, if we take the top of the path equaling 2.4 and down here is 0, then we've got a displacement that we're going to go through is negative 2.4 meters. Sorry, I'll just redo that one there. So someone's just coming through the lab. So that's, sorry, this is 0. And remember, when we do a drop, everything below our dropping point is a negative S. So this would be negative 2.4. That's probably a better way of describing what I just said. And we do not know the time. So using that, we've got SV squared equals U squared plus 2AS. And popping these values in, we get V squared equals 0 plus 2 times negative 9.8 times negative 2.4. And that's going to get hidden by there. Let's keep on going. And that means that V squared would equal, just calculating this, 2 times 9.8 times 2.4. The negatives will cancel there. We get 47.04. Okay, and if you notice, we've got V squared equaling that value there again, and it's the same thing here. Okay, so that leaves us with V equaling 6.9 meters per second, because since we've got to this point here, hit the same when we square root. So we can do this problem by the equations of motion using UVAST, or we can do it with using energies and conserve mechanical energy. The same thing happens when we throw the ball in the vertical direction. So question 3 is a 100-gram ball is thrown vertically with a velocity of 8 meters per second. What's the initial kinetic energy of the ball? Okay, and then we're going to work out its gravitational potential at the end, the top of the flight. So let's have a look at what we're doing. So here is our ball. This time we're throwing it vertically, okay, and we know that we're going to work out the kinetic energy at the bottom. We're going to make this the 0 level. If this is the 0 level, what do we know about our U? Our U, our gravitational potential energy, would equal 0. So our total kinetic energy, EM, would equal whatever value we have here for kinetic energy plus 0. So let's work out the kinetic energy, because it asks us to do what is the initial kinetic energy. So 3A, the kinetic energy initially would be a half mv squared. It's a half. Now the mass of this ball here is 100 grams, so it's 0.1 kilograms, and its velocity is 8 meters per second, so it's 8 squared. So that would be 0.5 times 0.1 times 64, and it is 3.2. So it's 3.2 joules. So the total mechanical energy it has at the bottom of the path is 3.2 joules. It must have the same amount of mechanical energy at every point as it goes up. At the top of the path, my kinetic energy will be 0, because at the top of the path, the velocity of the ball would reduce down to 0. So what would be the potential energy? It would be 3.2 joules. Once again, EM would be conserved as 3.2 joules. So as a result, if I know that the potential energy at the top of the path is 3.2 joules, I can find, because we know that U equals mg delta H, I can use this to find delta H. So determine the height to which it rises. This means that that's 3.2, and this would be 0.1 times 9.8 times delta H. So delta H would equal 3.2 on 0.1 times 9.8. Calculating that now. So 3.2 over 0.1 times 9.8, and that's 3.3 meters. It's actually 3.26. Let's just say it's 3.3, close enough, meters in height. Okay. Moving on to question 4 now, which is the pendulum one. I've gone through a pendulum one on the board before, so let's have a look at quickly doing one of these, and I might just abandon it halfway through so you can have a go yourself. The pendulum has a length of 1.2 meters. So when it hangs straight down, it's 1.2 meters. It has a mass of 300 grams, so 0.3 kilograms. And when it drawn back an angle of theta, it rises through a vertical displacement of 20 centimeters or 0.2 meters. Okay. So we can now work out the change in gravitational potential energy. Once again, we're going to set this here as the 0 reference line. And that means at that point there, we can consider U to equaling 0. At this point up here, U can equal something else. U equals mg delta H, and delta H is 0.2 meters. We know m is that. So have a go at yourself to calculate the potential energy of the pendulum at the top and then at its equilibrium point. Now, the equilibrium point is at its lowest point. This is what we call the equilibrium point. And at that point here, all the kinetic energy, so all the gravitational potential energy has been converted into potential energy. I'll say that again because that's not right. All the potential energy has been converted into kinetic energy. So down here, U equals 0 and K is the same value as this one up here. So have a go at doing that one yourself. The same thing is going to happen with question 5, so I'll skip that. Let's try question 6 because it is a slight variant to this one here, and I'll just start you off and hopefully you can continue with it. Question 6 is the pendulum, here it is being brought back through an angle of 15 degrees. Okay. As a result, you have to calculate using, we know it's a 2 meter pendulum, so it's 2, and that is 2 there. We need to calculate this height here. Okay. I'm not going to spoil it for you because it's just using trigonometry, but have a go at doing that. And then once you've found that, you can apply the same things that you've just done in questions 4 and 5 to find its velocity as it passes through the equilibrium point. Okay, I hope you're successful. If you do need me to do a full solution of question 6, please let me know by emailing me. Thank you.